So, what we're doing today is called linear correlation and regression. What does that mean? Well, the idea of this topic is that you're going to describe the relationship between two different variables. And we're not doing everything in the book, we're just doing the highlights, what I've pulled out. Okay. So as we start this topic, I just want to make this comment. Number one, there are some really long and complicated calculations that could go into this topic. We're going to skip that. Guess what we're going to use instead? To replace doing the calculations by hand, we're going to use StatDisk. Okay. So that's the first thing. So when you look in the book, you're going to see these long formulas and calculations. We're not doing that stuff. That's the first thing. Yeah, that's the only thing. Okay. Okay. So let's break this down. First of all, what does correlation mean? I'm sorry. The other thing, I don't remember what it was. The other thing is we're now going to look at two separate variables. Up until this point in the course, we've only talked about one variable. We only talked about measuring exam scores or asking for responses to one particular question. What we're going to do right now is talk about the relationship between two different amounts. So what is that talking about? What does correlation mean? It means that you have two variables and one is related to the other. Or to be more mathematically precise, correlation means you have two quantitative variables, and saying they are linearly correlated means that as one variable goes up, the other variable tends to go up or down. And again, we'll call it linear mean straight line. So can you guys give me an example of two things that you could measure that might be correlated? As one of them goes up, the other one goes up, or it goes down. Yeah. There you go, perfect. Number of cigarettes that you smoked, and I guess you could say whether or not you get cancer or the likelihood of getting cancer. Absolutely. So the more cigarettes, the more likely cancer is. Okay. So that's a good example. Yeah, Anna. Okay, good. There you go. So how can we measure how much you eat in a number? I would say how many calories you intake. So number of calories that you intake and amount of weight that you gain. Absolutely. Okay. So yeah, so those are two really good examples. One example that I came up with is years of employment versus salary. So what would you say is the relationship between these two things? There you go. The longer you work, or the more years that you've worked, the higher your salary is. Absolutely. And I want to point out one thing in this example and also Anna's example. We tend to think of these relationships in one direction, usually. So we wouldn't say that the more money you make, then the more years of experience you have. That doesn't make sense. We tend to think of, if you tell me how many years you've worked, then I can tell you what your salary is. Same thing with Anna's example. We would tend to say, if you tell me how many calories you eat, then I can tell you how much weight you're likely to gain, and not the other way around. Does that make sense? Y'all? Okay. So what this means is that we're going to tend to think of, for example, years of employment and salary. Years of employment is the input and salary is the output, which, as we're going to see, means that years of employment is represented by your X and salary is represented by your Y. Okay. So What is a positive correlation? If one goes up, the other tends to go up. So what's a negative correlation? Yeah, exactly. You have to be careful about how you say it, right? If one goes up, then the other tends to go down. Notice that if you say if one goes down, the other goes down, that's the same as saying what? If one goes up, the other goes up. That's the same thing. So you have to make sure that you say it like this.
That's what the first one says. It says one goes up, the other one goes up.
Right. And so negative correlation is if one goes up, the other tends to go down. Alright. Alright. So the next thing I'm going to show you is I'm going to show you how we can represent our data visually. Now keep in mind what we're trying to represent. For example, in this last example, years of employment and salary. Both of those numbers correspond to one person answering two separate questions. So you'd want to have these values paired off in some way, an x value and a y value. Now how can you represent that on a graph? So for example, if one person has worked 7 years and their salary is $48,000, how would you represent that on a graph? Sorry? So where would you mark years? On the x-axis, and where would you mark salary? On the y-axis, and then how would you mark this data down on the graph? Put a point there. So we're used to thinking of graphs as like lines or whatever, but here we have individual values, so we're going to mark off points. So for example, this is I forget what data was being represented here, but this point represents what data values? This is not years and salary, so I forget what the numbers represent. But what numbers are represented by that dot? Okay, so approximately 9,600. So which one's x, which one's y? 9,000 is your x. That's on the x-axis. Okay. So is this okay? Data on a graph, and so the graph with just the dots, that's called a scatter plot. And by the way, you can make these in Excel or any spreadsheet. Sorry?
That's a scatter plot?
Yes, scatter plot. Okay. Now, this graph is already marked up. So let's refer to what we've got here. What would you say is the relationship between, looking at the dots, what's the relationship between the x variable and the y variable in this case? First of all, would you say that they're correlated? Is there any kind of relationship between x values and y values? Yes, no? Let me put it this way. As x goes up, as x values get bigger, can you say something about y values? They also get bigger. So what's that called? Positive correlation. All right. Okay. So once we recognize that as x goes up, y goes up, we have a positive correlation. So the next thing we want to talk about is what's called the line of best fit. So what we want to do is we want to say, well, there's approximately a straight line, or there's a straight line which approximates our data. So on this graph, which line is that? What color is the line that approximates the data? It's the black line. So this one going from bottom left to upper right. Okay. Does everyone see how this line kind of approximates the data, but not exactly?
Yeah, because it goes along with the balance.
Right. So the idea is that we're trying to draw a straight line that kind of follows the pattern of the dots, but it has to be a straight line. So is this straight line a reasonable approximation of the dots? Yes. Is it an exact version of the dots? No, it's not. Okay. So this straight line is called the line of best fit, which is also called the regression line. All right. So we've already covered in broad detail the two topics for today: correlation and regression. You can see that x and y are positively correlated, and you can see that there's this line of best fit. Any questions on those basic ideas? Okay. The next thing is we're going to figure out how can we describe these things mathematically. Okay. So the number that measures how correlated the number that measures the amount of correlation between x and y is called R. R is the linear correlation coefficient. So what the heck is R? R will be positive if, as x goes up, y goes up, which is called positive correlation. And can you guess what the next thing is?
Will be negative if x goes up.
There you go. R will be negative if, as x goes up, y goes down, which represents negative correlation. Okay. Now, in addition, if the relationship is exactly linear, in other words, if all points are exactly on a straight line, then R will be 1. Or negative 1. When would R be positive 1 as opposed to negative 1? Yeah, because R is going to be positive when it's going up. So if you have a straight line going up, R is going to be positive 1. And then what's the other case?
Going down.
If you have
The line going down.
a straight line, all the dots in a straight line going down, R is negative 1. Okay. Now, if there is no linear relationship whatsoever, then R is 0. And furthermore, all R values are from negative 1 to 1. Line. So your R is very close to negative 1. Same thing for this line. It's steeper, but R doesn't care about steepness. R just says how close to a straight line do we have. So again, we guess negative 1, and that's very close. So R is just measuring how close is it to being in a straight line. Okay. So what measures the steepness is the slope, which hopefully you all remember from algebra. But more on that in a minute. Okay. So for example, let's look at these three graphs right here. Excuse me. Well, let's look at example 1 and example 3. Now, what could you say about the line of best fit in graph 1 and graph 3? What can you tell me about the line itself? The line itself, the line of best fit, is about the same. Are the R's the same? Okay, well, similar. So compare the R for the first one versus the R for the third one.
The third one there was more scattered.
I'm sorry?
The third one there was scattered.
The third one is more scattered. So give me an approximate R value for the first one. 0.99, 0.95, something like that. Give me an R value for the third one. 0.80. Okay. So it turns out for the first one we got R of 0.946, and the second one, the third graph, is R of 0.787. So again, notice the line of best fit is exactly the same. R is simply measuring how close are the dots to the line. And the slope is something else entirely. The slope is the slope of the line. Okay. Next. So R measures this in a way we haven't done the exact calculations. We're going to skip that part. There's also R squared, and this is called the coefficient of determination. This measures the proportion of the variation from the mean predicted by the line of best fit. So, first of all, how do you think you calculate it? What's the name of it? You take R and square it. Exactly. Now, what does R squared mean? We're going to come back to that and talk about that a little bit later to get a better. I realize that this just sounds like a bunch of words right now. We're going to come back and talk about variation and prediction and all that in a little bit. Okay. But let's just notice some properties of R squared from what we know about R. If R squared equals 1, what does that tell you? It's a what? If R squared is 1, then what was R? It was 1 or negative 1. So what does it tell you about your data? Sorry? Perfect straight line. Exactly. Now if R squared is 0, then what was R? It's 0. So what does that tell you about your data? It's not even close to straight line. It's very scattered.